In this video, we will discuss some techniques that do not have an explicit name but are very useful in solving some dynamic programming problems that involve grid and traversals on grid. You might have heard of the classic LeetCode problem where you are standing at the first cell of the grid and your goal is to reach the last cell of the grid, and in one step you can either move to the right or you can move downwards, and you have to maximize the profit that you accumulate by traversing through all of these cells. So for example, this is one possible path and the profit is the value that you have accumulated from each of the cells that you have visited. So you will remember that this is the most classical famous problem for dynamic programming on a 2D grid. Now in this video, I want to discuss a variation of that problem where ask you what is the maximum profit that you can get if I select any random cell from the grid. Suppose this cell that I selected is this one, which is highlighted with X, and I replace this value with Y. So X gets converted to Y. Now you see that the grid has changed because one entry is different. Now, can you find out the maximum profit that you can accumulate in the new grid? Of course, you can do it in O of R into C for each query. But can you do it in O of 1 for each query? So in this video, I want to show you a beautiful technique using which you can do that. So let's start out with the simplest DP definition that you might have to solve this problem. So for the LeetCode problem, wherein you are not given any modifications of the grid, how do you solve that problem? You start out with, let's pick a grid. You start out with this DP definition where you say DP of ij is the max profit to reach R comma C, or let's say, yeah, to reach R comma C. This is the DP definition that you have. And how do you perform the DP transitions? So if you are interested in the DP value of this particular cell, if you are interested in the DP value of this cell, so from this cell you ask the question, okay, DP definition, let me write it down completely. DPij is the max profit to reach R comma C when you start your journey at cell I comma j. This is the actual DP definition that you use in the LeetCode problem. And how do you populate this DP value? You can see that when you are at this cell, you can make two choices. You can either go to the right or you can go down. But once you have gone to the right, once you are at this cell, you are interested in asking the same question, that from this cell, which is I comma j plus 1, what is the maximum profit that you can get? Or from this cell, which is I plus 1 comma j, what is the maximum profit that you can get? So your DP transitions look like DP of ij is equal to A of ij, because since you are standing on that cell, you will have to take the profit of that cell plus max of dp I plus 1j comma dp I comma j plus 1. Okay, so and you can see that each dp value relies on a cell that is downwards and a cell that is on the right hand side. So if you try to fill the dp values in this fashion, you start from the bottom cell and you do it in this fashion. You fill this last row from right to left, and then the second last row from right to left, and so on. So by the time you arrive over here, you will already have the DP value of this cell, and you will also have the DP value of this cell. So nothing new here. I'm just restating the facts that you used to solve the classical LeetCode problem. Now we will make some DP definition changes, but the idea will be exactly the same as this problem. So this time, let's define two different kind of DP. So this time you have only defined that from this cell, what is the profit that you can get when you finally reach the last cell. So let us define this DP as a start DP. So we define something known as a start DP. So this is nothing but your start DP. So start DP of ij means what is the max profit that you can get when you start your journey at cell ij and your goal is to reach cell r comma c. So on similar veins, let's define something known as an end DP. So here I will label it as start DP. Okay. And here let's define end DP of ij is the maximum profit that you can get when you end your when you end your journey at cell I comma j. So this is your DP definition for the end DP. This means that this time we are not starting from a cell, but we are asking that assume that you always start from 1 comma 1. Here the assumption was that you always end at r comma c, but now the assumption is that you always start at the cell 1 comma 1, but you don't end your journey over here. You might end your journey over here. This is cell I comma j. So this is I comma j. So what is the profit that you can get when you want to end your journey over here? So that's why we have defined it as end DP of ij is the maximum profit that you can get when you end your journey at cell ij. So what will the transitions be? You can see that the transition is nearly the same. That if you want to end your journey over here, what is your penultimate move? You must have either come from here or you must have arrived at this cell from here. Means you are interested in the maximum profit that you can accumulate when you end your journey at this cell and then you will take one step forward, or the maximum profit that you can accumulate when you end your journey at this cell and then you will take one step forward. So end DP of I is nothing but A of ij plus max of DP I minus 1j comma DP I j minus 1. And in this end DP variation, what will the answer to the original problem be, wherein you wanted to start from this cell but wanted to end at this cell? So your in this version, your answer would be end DP of r comma c. And in the start DP version, your answer would have been start DP of 1 comma 1. So you see that it's just a matter of preference. So some people like to define it as a start DP and some people like to define it as an end DP, and both of them are correct way to solve the original LeetCode problem. But the reason why I'm introducing both the ways is that we'll see a very cool trick that combines both of these ways to answer some queries wherein you are allowed to modify the values on the cell. So now we know that for any cell, we can answer a lot of queries. So initial query was only what is the maximum profit that you can get when you have to start from this cell and you have to end at this cell. But now you can also answer for any given cell what is the maximum profit that you can accumulate when you have to end your journey over here. And you can also answer partial queries like what is the maximum profit that you can get when you start your journey from here not at 1 comma 1. And all of these can be answered in O of 1. Why? Because all the DP values you have already stored and cached somewhere in the start DP and the end DP table. So now let's ask another question that okay, for each cell you will be able to answer what is the maximum profit that you can get if you start your journey at that cell or if you end your journey at that cell. But now if I ask you the question that this is your starting cell, this is fixed, and this is your ending cell, this is also fixed, and I ask you that you have to necessarily cross this cell. Suppose this cell is I comma j. So I tell you that there are multiple possible paths that can exist on this grid that lead from this to this, but you have to only consider the paths that cross through this vertex and then eventually reaches here. So can you find out the maximum profit that crosses any given path for sure? So how do you do that? So to do that, we define something known as a cross DP. So this is the start DP, this is the end DP. Now let's define a cross DP. So cross DP of IJ means the max profit that you can get if you have to necessarily cross cell I comma j. Now how do you do the DP transitions for these? So the DP transition for start DP and end DP was easy, but how do you figure out the answer for cross DP? So you will realize this cross DP is nothing but since this is just a milestone in your journey, then you would want to maximize the profit before you reach this milestone, and you want to maximize the profit after you started your journey again from your milestone. So this is like your resting point. So of course you want to be greedy, you want to find out the best profit that you can get before you reach your resting point and the best profit that you can get after you have rested for a while. So this means that you are interested in asking the question, what is the maximum profit that you can get when you start from here and you end over here? This is nothing but your end DP, which we have already computed. End DP denotes exactly what we are looking for. And the next question that you are looking for is, what is the maximum profit that you can get when you start your journey over here and you end your journey over here? So this is nothing but the start DP that we have already computed. But one thing we have double counted, which is the value on this cell that is at I comma j, because that has been included in start DP as well as the end DP. So the transitions would very simply be for cross DP, it's the easiest transition. So cross DP of I comma j is nothing but start DP of I comma j plus end DP of I comma j minus A of I comma j. So this is the simplest transition for the cross DP. So now that you have this start DP, end DP and cross DP, then you have some very powerful tools available with you. So we have already discussed some techniques now that can help you solve some problems, right? It's not just about finding the best path from start to finish, but it's also about having the answer to all the intermediate questions that anyone might ask. Like if anyone now asks you, what is the best path that you can get that crosses this vertex? Now you know how to solve it. And how can you do that? Via cross DP. So now let's learn some more tricks. So, and this might be the like novelty part of the video, which you might have not known about before. So let's focus on our journey. So suppose we are at this cell and this is the cell I comma j. So in one step, what are the transitions that we can make? So we can either go right, meaning the j increases by 1, or we can go down. This means I increases by 1. So first let's write it down in plain English what is happening. So we can say either I increases by 1 or j increases by 1. But this is a lot of if else either or etc. Can we compress both of these expression into one? So can we compress this and just state a single English statement that would uh, combine both of these mathematical expressions? So the statement that you can make is, since exactly one of them is increasing, then if you look at the number called I plus j, so this number you can say will definitely increase by exactly 1. So instead of saying this that either I increases by 1 or j increases by 1, can you see why it is identical to just say I plus j increases by 1? So now what do we do with this interpretation? Right? We know that in each movement that you make, I plus j will necessarily increase by 1. Okay, that's fine. But now what does I plus j look like on a grid? Right? So if you are coming from a maths background, and if I ask you, what does I plus j look like on a grid? What do the cells which have the same I plus j look like on a grid? So let's see. You will realize that I plus j is nothing but the series of antidiagonals. So let me write that down. This is nothing but antidiagonals. So antidiagonals are basically these diagonals that you see on the screen, and each cell that is colored with the same antidiagonal will have the same I plus j. So that's why you can see that when you started your journey over here, you can either move to the right or you can move downwards. So you can see that no matter where you move, you you move from one antidiagonal to the second antidiagonal, right? So let's define all of these antidiagonals by D. So D represents the antidiagonal, and each antidiagonal can be uniquely identified by the value of I plus j. So let's say D is equal to 0 or D is equal to, so here the first antidiagonal has 1 comma 1, right? So that will be D is equal to 2. The second antidiagonal has 2 comma 1, so that will be D is equal to 3. So you can see that each D represents one antidiagonal on this matrix. Now let's look at any random position. Let's suppose that you are over here. This means that you are on the antidiagonal that is represented by this color green. But once you make a move, you will either land on this teal antidiagonal or you will land on this teal antidiagonal. So what can we conclude? So now we know that the problem is asking us in other ways to move from one antidiagonal to another, right? So that is why in one step you are on d is equal to 2, and then you move to d is equal to 3, and then you move to d is equal to 4, and so on. So this is a very interesting way to visualize that this pattern moving right and moving down is equal to switching the antidiagonal, like moving from this antidiagonal to this one. So this is one observation that we have made. that we have made, what are the other observations that you can make? So you can see that in one operation, you necessarily have to move to the next anti-diagonal. This means that if you select any anti-diagonal, suppose you select this yellow anti-diagonal, then you can conclude that it is not possible to visit two cells on the same anti-diagonal. Why? Because we have just saw that one move is equivalent to moving to the next anti-diagonal. So if you first came to this element in this anti-diagonal, then after you move to this anti-diagonal, there is no way to come back. So the conclusion that you can make, is the original path looks like a series of moves from one anti-diagonal to the next. In fact, this statement is a bit more strict in the sense that you can't visit two cells on the same anti-diagonal. And I hope that's clear why you can't visit two cells, because that is the crux of the algorithm. Because in this figure, you can see that if you are standing on this cell, then you have to move to this anti-diagonal. So the movement is always along an anti-diagonal. So you, in one operation, you always have to go to the next anti-diagonal and there is no way to go back. So that's why if you have visited this cell, then you cannot visit any other cells in this anti-diagonal. And since we know that in each operation, D increases by exactly 1, so there is no way that you can miss any anti-diagonal. So you have to start with this anti-diagonal, then go to one element in this anti-diagonal, then exactly one element in this anti-diagonal, then exactly one element in this anti-diagonal, and so on. So now let's devise the final algorithm where I'm interested in knowing what happens if I swap some values in the grid and I still ask you the original question, what is the best profit that you can get. So you have this grid and suppose you were planning to modify this cell I comma j. Now let's look at this cell, and once you have modified the value on this cell, then the optimal path, it can either traverse through this cell that you have just modified. So suppose this is the optimal path. So if it really is the optimal path, then you know that since you only modified this particular cell, then this this end dp of ij, that will this end dp of ij, this means what is the best profit to reach over here. So you can have this end dp of ij, and then you can go from here to the last cell via start dp of ij. And you know that something has been double counted, but the thing that was double counted, which was your x that was written over here previously. So it is counted in end dp, so let's remove it. And it's counted in start dp, let's remove it. And we should have counted only y once, right? So this will be your answer if the path crosses the cell that you just changed. So if you know for sure that the path crosses the cell that you just changed, then the answer will be simply start dp of ij, end dp of ij, you subtract the older value and then you add the newer value. But what if this cell that you just changed, what if it does not pass through I comma j? So what if the optimal path does not pass through I comma j? Now you might think that, okay, it's very simple. If it does not pass through I comma j, then the answer should not change. On the original grid, you already have the answer to start dp 1 comma 1, right? So can you not use the answer from before? So the answer is that no, you cannot use this from before, because you don't know whether in start dp you don't actually have the information whether the maximum profit in start dp 1 comma 1, whether it actually passed through this cell or not. If you remember, we never calculated the benefit that you get when you do not cross that cell. We only calculated the benefit when you cross a particular cell. So we know that if you do cross this cell that was just changed, then the answer you can get for sure. But now what about the last case where you do not cross this cell? And this is where the concept of anti-diagonal will come into play. So consider this anti-diagonal, right? Let me draw this correctly. So this is the first anti-diagonal, and then this is the second one, and this is the third one. So let's consider this anti-diagonal, and suppose this is the cell that you are dealing with. Then if you have not crossed this cell, this means that by our previous discussion, you must have crossed exactly one element on this anti-diagonal. So it should have been either this one and this one and this one. And since you have not crossed this element and you have crossed some other element on this anti-diagonal, then even if you change the value of this element, it will not matter, because you are not going to cross this element. So this means that if you want to compute the profit when you want to exclude an element, when you want to guarantee that you do not pass this element, all you have to do is find out the best possible path when you cross any of the anti-diagonal elements. So this is the reason why we had defined that cross dp. If you remember, so in this cross dp, we had said that what is the profit that you can get when you necessarily pass through that element. And now we know that if this is an element, then if you don't pass this element, if you don't cross through this element, then you will have to cross through one of the anti-diagonal elements. You will have to cross through either this one or this one. So all you have to do is, for the cells that you are changing, so if this is the cell that you are changing, then you simply look at all the anti-diagonal elements and compute their best cross dp on the anti-diagonal. Now it might look like an O of length of the anti-diagonal time, because you will have to traverse that entire anti-diagonal and then compute the cross dp. But if you think about it, the cross dp does not change. So, and every time you change an x, you only have to keep track of the maximum and the second maximum element for each anti-diagonal. So for example, if you are dealing with this anti-diagonal, let's say, then if I change one element on this anti-diagonal, so if I switch it from x to y, then you don't necessarily need to travel all the elements on this anti-diagonal. For each anti-diagonal, you can pre-compute the max and the second max. So if the max is not on this element, then of course that max will still remain the max. But if the max is on this element which was just changed, right, and you cannot take this element, then you find out which is the second max, right, and you know that going through that anti-diagonal element will give you the best path. So the final answer is nothing but when you change x to y, right, you either cross ij, right? So the answer will simply be cross ij. So sorry, if you want to cross ij, then the answer will be uh, start of ij plus end of ij minus x plus y. This is when you want to cross ij. And when you want to don't cross ij, then max on the anti-diagonal, which is nothing but cross I star comma j star, where I star comma j stars are the cells on the anti-diagonal for cells on the same anti-diagonal as I comma j. And using this, you can see that you now have an O of one algorithm to answer queries that can change one cell, any cell that it wants. Let me know in the comment section if you want to upsolve this problem. I will link the problem in the comment section or the YouTube description. Thank you.